This video corresponds with section 11.11 of your textbook, which covers periodicity and trends in the periodic table. When we talk about trends, we generally are referring to something across a period on the periodic table, which means a row. Remember, period 3 would be starting with sodium and working across to argon. Or we talk about up and down within a group or family, like the hydrogen family, for example. So the first trend we'll talk about is trend in atomic radius, or size of the atom. And it does something a little bit surprising as you go left to right on the periodic table. In other words, as you go across a period, the atom actually gets smaller. Let's take sodium again and work our way across to argon. It seems counterintuitive that you would be cramming more and more electrons into an atom going from left to right, and the atom actually gets smaller instead of getting larger. You'd expect the repulsion of the electrons to increase and the atom would get larger. But in fact, we see the opposite. Here is a chart right out of your book that shows the atomic radius as you go left to right. And here's sodium, magnesium, aluminum, and this is consistent for every period or row on the periodic table, that the atom gets smaller and smaller as you go from left to right and increase the number of electrons. So why? What's going on here? Well, what is actually observed is that as n stays the same, remember n is row number on the periodic table, and you can think of that also as the shell or the layer of the onion, the energy level. That energy level stays the same, and you're cramming more and more electrons into that energy level. Sorry for the video. While it's true that we're increasing the number of electrons, we are also increasing the number of protons. So we're increasing the number of electrons in that energy level, but the attraction to that increased number of protons gets bigger and bigger as you go across from left to right. So more protons from left to right in this row means that the attraction to those protons is greater. So while it's true there are more electrons, the atom does get smaller and smaller as we go left to right because there are more protons and more attraction. Now the second trend in atomic radius is within a group or family. So up and down the periodic table, the radius generally increases as you go down a group. And I think that's obvious. So let's look at the hydrogen family, in other words, the alkaline earth metals. The radius always increase as you go top to bottom. And that's simply because the number of energy levels increases as we go from top to bottom on the periodic table. So the shells or number of layers of the onion increases as you go from top to bottom. And that's, again, the case for all of the representative elements. The atom simply gets bigger within a family from top to bottom. Now let's look at ionic radius instead of atomic radius. A couple things to remember. First of all, cations are positive. They lose electrons. And cations always get smaller than the atom. And that should be obvious because you're losing something, you're losing a negative, but it also is because there is no change to the nucleus. The number of protons in the nucleus stays the same. And if you lose a negative, the attractive power of that positive nucleus, which is unchanged, is greater. And so the cation, the cation, actually gets smaller. Now let's look at some pictures of this. This is a table that's worth a little bit of explaining. Let me make it smaller so that we can see it on one slide right here. Notice that here's the key here on the right, and the key tells us that the neutral atoms are shown in gray. So on all of these, either cation, which is on the left, or anions, the nonmetals, on the right. The gray is the size of the atom. And the pink, in this case, is the size of the cation. And no matter which cation you look at, the cation is always smaller than the neutral atom. Because again, you're losing negatives, and the attraction to the positive nucleus is therefore relatively greater because the positives in the nucleus are unchanged. So cations get smaller. Anions, as you can see, the opposite is true. The anion gains negatives, gains the negative electrons. And therefore the repulsion between those electrons is greater, and the anions are always greater than the neutral atom. And that is shown here, I believe. Let's make sure we copy these notes down. The anions are negative, they gain electrons, and the anionic radius is always larger than the atomic radius. And again, that's because there's more repulsion by the increased number of electrons. It has nothing to do with the positives in the nucleus this time. All right, other trends in the periodic table. Ions get larger as you go down a group, and that should be obvious as well, for the same reason that atoms get larger as you go down a group or a family. So let's take the beryllium group, for example. Notice on this chart here, the numbers shown in pink and in gray and in blue for the anions are the actual atomic or ionic radii in angstroms up here. An angstrom is a tenth of a nanometer, so 10 to the negative 10th of a meter. It's just another measure of length. So in any event, notice that even for the +2 ions, they always get bigger as you go down the periodic table. Here's the +1, the alkali metals. They always get bigger, again, simply because the principal quantum number, rho number, or if you like, energy levels or shells, gets bigger as you go down a group. Now, other trends in periodic trends in the cations. The cations decrease in size from left to right, and that's because they are losing progressively more electrons. So let's go back again to this chart, and let's look at sodium, magnesium, aluminum, a +1, +2, +3 ion, meaning cation, meaning it's lost 1, 2, and 3 electrons. So, of course, the nucleus stays the same, so the attractive force to that nucleus becomes progressively greater as you lose 1, 2, or 3 electrons, forming cations. So the cations get smaller and smaller. But notice what happens to the size of the anion, which is the blue, compared to the gray, which is the neutral atom. The anion gets larger. So the trend in ionic radius is to get smaller with the cations, to get larger again, and then smaller again. And let's talk a little bit about that. So the periodic trends in cations is decrease in size from +1 to +2 and +3. That's because they lose more electrons from left to right. Anions also do the same thing. They decrease in size from left to right as we go -3, -2, and -1. Now on this chart, I want you to notice that the -3 ions are not shown. To the left of the oxygen family is, of course, the nitrogen family. Let me show you the periodic table. There's nitrogen. And while nitrogen tends to form covalent bonds, which we'll talk about next chapter, it does form ions on occasion. And this will form a -3. Oxygen, as you know, is a -2, and other elements in that family. And fluorine and the halogens form a -1. So the trend is a -3, -2, -1. And of course, a -3 ion is considerably bigger than its neutral atom. And then a -2 ion, yeah, it's gaining 2 electrons, it's gaining size because of repulsion, but it won't be as big as a -3. So let's look again at this picture, which shows, again, nitrogen family is not shown, but the oxygen 2- is bigger than the fluorine 1-. Look at the numbers, 1.26 angstroms versus 1.19. And the sulfur 2- is bigger than the chlorine 1-. So there is another trend in anions that the groups 5 through 7, which gain 3, 2, and then 1 electron, decrease in size, also decrease in size from left to right. So the more electrons that an atom has gained to become an ion, the larger it is. So let's take a look again at that chart. That the overall ionic radius goes +1, +2, +3, getting smaller and smaller as it loses electrons, and then it gains a huge amount of volume as it gains 3 electrons. That's not shown for, let's see, that would be phosphorus, and then 2 electrons for sulfur, and 1 electron for the chlorine -. So the trend is it gets larger as it becomes a +1 and smaller slowly, and then it gets larger as it becomes a -3 and smaller slowly to the right. So it's kind of an unusual trend. All right, this is a new concept, but it is another important trend on the periodic table, and that's ionization energy, and I'll shorthand that by calling it IE, ionization energy. Now, ionization energy is defined as this: the energy needed to remove one electron from an atom. And that is always a positive quantity. It is always endothermic to yank one electron off of an atom. So elements with large ionization energies are elements that have very strong holds on electrons, things that don't tend to give up electrons easily. So think in your mind for a second, what are the elements that don't ionize, that tend to not form ions? Look at the periodic table, and I hope you are thinking about the noble gases. The noble gases don't react, they don't give up or take in electrons because they have complete S and P sublevels in their highest principal quantum number. In other words, full electrons, full valence electron shells. So they have very low ionization energies. I'm sorry, very high ionization energies. They strongly hold on to their electrons. But just behind them, also with really high ionization energies, are the things, the elements that tend to form anions. In other words, they don't give up electrons, they take in electrons. So the halogens, fluorine, chlorine, etc., are one electron away from that satisfied octet in the valence electrons, forming an F minus, a Cl minus. So they don't tend to give up electrons. In fact, they do just the opposite. They tend to take in electrons. So they have very large ionization energies too. Noble gases and the group 7A have high ionization energies. These are the things that aren't likely to form cations. They don't give up electrons easily. In fact, quite the opposite. They much more strongly prefer to take in electrons. So they have large ionization energies. Now, as you might imagine, the things that have the smallest ionization energies are the things that tend to lose electrons the easiest. And as I'm sure you know, those are the metals. Metals form cations, right? So we can say all metals have relatively low ionization energies compared to non-metals, which tend to form anions. These guys give up electrons. They form positive ions, so they have low ionization energies. What has the lowest? The lowest ionization energies are the things that most easily give up their electrons. So you'd expect the lowest ionization energies are the things that form +1, the alkali metals, or +2, the alkaline earth metals. Now, ionization energies come in a series. We've been talking so far about what's called the first ionization energy, and it sounds like what it is. The first ionization energy is the energy you need to yank just one electron, the first electron, away from an atom. But what about the second ionization energy? How much energy would it take to pull a second second electron off of an atom? Or a third electron? So these have sequential names: the first ionization energy, the second, the third ionization energy, etc. And there is a trend in those ionization energies as well. The second ionization energy is always greater than the first ionization energy. So let me go back. Oh, you know what? Let's take a look at a couple pictures here. First, this is an interesting periodic table here. This shows the ionization energy depicted as height on the periodic table. So those elements with really high ionization energies, the noble gases and the halogens, are much higher than these elements down here. The lowest ionization energies, not surprisingly, are the alkali metals, which tend to form cations. There's a couple interesting things here. Notice that zinc and the zinc family have slightly higher ionization energies than gallium and germanium. Remember the stability of having a full D sublevel, 10 electrons in the D sublevel. A stable atom generally has a high ionization energy, meaning it's non-reactive. So this block of 10 elements having full D sublevels are quite stable and non-reactive, so they have a slightly higher ionization energy. Of course, helium and neon, being the smallest atoms in the noble gases, have the highest ionization energies, and fluorine has the highest ionization energy of anything that tends to form ions. So we can talk more about this a little later. Another kind of scary looking. Don't be scared. Kind of the scariest looking chart here is this. There's nothing much more I want to talk about other than this. This depicts the first ionization energies for every atom on the periodic table except for the F block. Okay, and what I really care about is that you notice the y-axis. This is ionization energy in kilojoules, and then the x-axis. Sorry, this is the y-axis, of course. The x-axis is simply atomic number, so increasing number of protons left to right. And look at the important bits here are, notice how high the ionization energies are for all of the noble gases. They have the highest ionization energies of anything in their families, in their groups. And the lowest ionization energy is take a noble gas and add 1 electron to it. So you're taking helium and you're going 1 more electron, which would be, of course, sodium. And we've learned that sodium, sorry, right here, sodium, there's neon, and go 1 past that to sodium, and you'll get a low ionization energy. Sorry, I think I skipped around there. But here is neon, very high ionization energy, noble gas, and there's sodium, the lowest ionization energy, because, again, wants to form cations. So the alkali metals have the lowest ionization energy of anything on the periodic table. Okay, where are we? Yes. So we're talking about ionization energies, first, second, and third ionization energies. And these are simply successive ionizations of a single atom. In other words, you pull 1 electron off, then you pull the second off. And there's always an increase. It's always endothermic, first of all, to remove an electron from a neutral atom. But the first ionization energy can be fairly low for things that form cations. Then there's the second ionization energy, which will always be higher than the first. The third IE will be higher than the second, etc., etc. And this kind of makes sense because the number of protons doesn't change. So as you remove electrons, the energy, the attractive force to that unchanging nucleus is greater and greater. So it takes more and more energy to remove the second or third electron. However, it's not smooth. It's not an incremental increase in energy as you pull off the first, the second, the third electron. In fact, there's a dramatic jump in ionization energy. Here's another table. Don't be scared. Let's talk about what it means. Let's go with the first. This is the period 3 elements. So let me scroll down. And the period 3 elements, of course, start with sodium and magnesium, aluminum, all the way over to argon. So it's a third row in the periodic table. And the ionization energy, look for sodium. The first ionization energy, pretty low. Second ionization energy, that's IE sub 2, huge increase, almost a 10-fold increase in the number of joules it would take to remove the second electron versus the first. Look at magnesium, the next one over in the row. 736 for the first, twice that for the second ionization energy, and then 5 times that amount of energy for the third electron to be removed. And this is the case for every element in that row. There becomes, let's look at phosphorus, 1,000, roughly 2, roughly 3, roughly 4,000. And then there's a jump from 6,000 to 21,000 joules to remove the 6th electron versus the 5th. So what's going on here? Why is it not smooth? Well, it has to do with the core electrons and the periodic table again. Let me bring this periodic table up here and make it a little bit larger so everyone can see it a little better. So back to this chart. Sodium. Let's remove electrons one at a time. Sodium is here on the periodic table. There's sodium. If I remove 1 electron, how many valence electrons does sodium have? Well, it's in the first family, or the first column of the periodic table. So it's got 1 valence electron. I remove that 1 valence electron, and look what's left. What's left behind is the noble gas configuration of neon. These are the core electrons. So it's only got 1 valence, and then you try to start pulling the second electron off, which is a core electron. It's really hard to do. There's a big energy jump from the first to the second ionization energy. Magnesium, same thing. It's got 2 valence electrons, and you try to take a third one off, which is a core electron. Well, that means you're doing the same thing. You pull 1 off, those are the 3s2, the 3s1 electron, and then you go to the 2p6, which is neon. Again, noble gas configuration. The core electrons have a huge energy increase. So let's just play around here and look at, let's say, phosphorus. Phosphorus, 1, 2, 3, 4, 5 valence electrons. The sixth one would be a core electron. So you had a huge jump in energy. And where's phosphorus? There it is. 1, 2, 3, 4, 5 valence electrons. The next one you try to pull off is a core electron from the configuration of neon. So it's going to be really difficult. So the ionization energies are related to whether an electron is a valence electron or not, and valence electrons are relatively easy to pull off, relatively low ionization energies. But when you get to a core electron inside the valence shell, then it's really difficult. The energies are huge to remove that core electron. All right, very last trend in the periodic table is something your book touches on. I don't tend to spend a lot of time on it, but it's called metallic character. It's kind of the opposite of ionization energy. This is the ease with which an atom loses an electron. So it's kind of the opposite of ionization energy, which is the energy you got to put in. So as you'd expect, this should say ionization energy, IE, not EN. What on the periodic table would you expect to most easily give up electrons? And that's, of course, the metals, the things that tend to form cations on the left side of the periodic table. And in fact, the things that have that most easily give up electrons are the things down here. That's francium, that's cesium. What's right above cesium? Rubidium. They are the most metallic metals. They most easily give up their electron, their first electron, which means they have the lowest ionization energies. Why is that? Remember, all of these elements in the alkali metals have one valence electron. And they also, the atomic radius gets bigger and bigger and bigger as we go down the periodic table. So there is those outer valence electrons, I should say that one outer valence electron, is further and further and further away from the positive nucleus. So the attraction to that nucleus is less and less. And therefore, it's easier to pull a negative electron away from that positive nucleus because it's further and further away. So the larger the atom, the lower the ionization energy. And we saw that on this chart as well, is that every single atom, the ionization energy decreases as you go down the periodic table. So the most metallic elements, the things that most easily give up their electrons, are here at the bottom left. And that concludes, oh, you know what, it doesn't quite conclude. I wanted to show you one more thing on the, to sort of summarize these trends, and that's this. And if you have your cameras out and it's a decent thing to take a picture of to remember. Of course, I'll save these notes online. But if you get a periodic table on a test, whether it's one of mine or whether it's a standardized test, what you should do is immediately start drawing some arrows on it. I would draw one like this that says our ionization energy, okay, increases from left to right. Okay, so ionization energy also does this. Okay, things like metallic character, you might draw an arrow like this that says metallic character. Okay, you might also draw an arrow that goes down like this, and that would be atomic radius. Okay, what else? There's a bunch of them. This summary slide right here shows you what you should kind of try to remember. Oh yeah, that's a good one. Let's not forget this one. That is really important. Atomic radius is larger on the left side and gets smaller to the right. So atomic radius is larger over here than it is over here. So I always think it's a good idea that the minute you get your periodic table and you know you're going to be asked questions about periodic trends, and that, by the way, is a really important subject on both the AP or the SAT too. Maybe the most important, along with stoichiometry, is your understanding of trends on the periodic table. Draw some arrows. Understand that ionization energy always increases to the right. Atomic radius always decreases to the right or increases to the left. The ionization energies increase to the top left. They decrease to the top right, decrease to the bottom left, etc. So take a picture of this slide. It's worth knowing, and that is the end of this video lesson.